Welcome back, Eastview Scholars. On this edition of Sharp Shorts, we're going to begin our series on how to name chemical compounds. This, I can't stress enough how important this is. This is the language of chemistry. And if you are going to be successful at all in chemistry, you have to be able to write and read the language. All the rest of the year, although you may understand what we're talking about, if you can't do this, you won't be able to get started on anything else. Anyhow, a quick reminder from our chemical bonds. Remember that a bond is just an attraction from the electrons of one. Certainly electrons are attracted to their own nucleus, but they can also be attracted to the nucleus of the things that they're bonded to, and that's kind of what a bond is. In a couple different forms that we did with ionic and covalent, that's what we went forward to. What we're going to start looking at here are ionic compounds, or at least compounds that follow ionic naming rules. When we get to the acid video, you'll see that while ionic compounds are defined as metals and nonmetals, hydrogen over here is unique. It could be in this column with its 1s, one orbital. It could also be in this column because it only needs one more to become helium, so it could be in the same column as the halogens. Anyhow, ionic bonds are metals and nonmetals, but acids by definition begin with a hydrogen. And so while they are really more of a covalent compound, they follow ionic rules. Anyhow, so ionic compounds by definition, and here was our old example, they one of the elements gives up an electron, like the sodium here wants to get rid of that one in its outer valence shell, and completely gets rid of that thing and becomes a positive cation, and the chlorine then picks up that electron because it wants one more out of its 7 to fill its shell and becomes a negative anion, and then it can form its crystal structure with intermolecular bonds. Okay. Here's the process we're going through. Here are all the compounds that follow ionic naming. Here we're looking at truly ionic compounds. Here, acids could be covalent, but they follow naming rules. Here's the key about ionic naming. It's driven by the number of elements and the cation, as we'll talk about at the very end of the series, how to identify. That's another important factor, is can I identify the separate things just by looking at them as whether they're binary, ternary, transition metals, or acids, bases. And the other key point, particularly if you still have some trouble determining ionic charges from their valence electrons, is that an ionic compound is always written with the cation, the metal first, and the anion, the nonmetal, second. So it's always metal first, the positive cation, nonmetal, negative anion, second. Okay? And that's what this talks about. Ionic bonds are formed when there's a complete transfer of valence electrons forming ions of either positive charge or a negative charge. The opposite charges create that electrostatic attraction, as a review of what we said before. For binary ionic compounds, and binary means two elements, as you saw in the chart before, you always in the anion in IDE. Okay? And just remember, cations are positive, and anions, well, they aren't negative, they're just misunderstood. Okay? So here's some examples, and what you can see here is that these are binary ionic compounds. Binary meaning they just have two elements. Two elements, two elements, two elements, two elements. Notice the IDE ending. And that's how we name them. Here's all you do. This is what it is. Here's your formula. All you do initially is name the cation. Its name is just what it is. So Na is sodium. Okay. And then you name the anion. Now the anion here is chlorine, but this is where you change the ending to identify it as a binary compound. You don't say chlorine, you say chloride. Now that one flows pretty smooth. It may happen on occasion that you say things wrong, like here. Our first cation, the metal, is magnesium. Oops, pen got away from me. Sorry. So I just say magnesium. And then P is phosphorus. And so it would be common, and it's okay when you start, that young folks would say phosphoride or something along that line. That's okay. We'll get used to it because we do it a bunch. But actually the name here is phosphide. Again, the key of it is it's two elements, and what identifies it as two elements 99.9% of the time is that ID ending. Okay. Now, when I go from words to formulas, here it's telling me what my two elements are. It's strontium, which is Sr, and that's going to be my positive cation. I'll have to figure out the charge in a second. And then bromine. Bromide is for bromine. IDE tells me to go look at the periodic table, and I know that's going to be negative. The other understanding here is all ionic compounds are neutral. So you have to have, connect and bond enough cations and anions that their total charge is zero. What do I mean by that? I mean that if I look at strontium, it has a +2 charge. It's in column 2 with 2 valence electrons. It wants to dump those 2 electrons, and in doing so, it'll have a +2 charge. Bromine is one of the halogens. It has 7 valence electrons. It's looking to pick up an electron, and so it will, and be a -1 charge. When these two then find that electrostatic attraction and create a bond, it needs to cancel out because compounds are neutral. So in reality, what's going to happen is one strontium will bind to 2 bromines, in order to have my total positive charge and my total negative charge cancel each other out. Okay? And so this formula is then written as SrBr, 2. 2 bromines for every 1 strontium. And that's what the subscripts tell you, is how many atoms of each are bonded together. And it's defined by how many negatives do I need with the positives to cancel things out. Okay? And we don't write the 1. Normally that's understood. We don't write the 1, so don't worry about that. If you're looking, what you notice is that the charge of 1 is the subscript of the other. Okay? So if you look at that, so we call that the charge flip-flop, which I'll illustrate here. Here we have aluminum, which is Al, and if you look it up, that's a +3 charge. I know it's plus because it's first, it's the metal, and it's got 3 valence electrons. Sulfur is S. It's in the same column as oxygen. It has 6 valence electrons, so it's going to want to pick up 2 extra. Okay. So I have a +3 and a -2, and I have to cancel those out. This is what we call the charge flip-flop, is that the charge of one element denotes the subscript of the other. So I'm going to need 2 aluminum and 3 sulfur. Why is that? Because the lowest common multiple is for these is 6. So if I have 2 aluminums, that's a +6. If I have 3 sulfur, that's a -6, and that cancels out. So the charge flip-flop works wonderfully. The one thing to make sure that you're careful of, though, is it's always, those subscripts are always the lowest possible ratio, because that's how they will bond together. And here's where I'll give you an example. Here's magnesium, which is a +2, and oxygen, which is a -2. And that's a metal and a nonmetal. It'll form an ionic compound. But the correct formula, pardon me, let me clear that up. The stylus is doing its own unique stuff. If I did the charge flip-flop, that would tell me that both would be written with a 2. But that's not my lowest ratio. Okay? If they're both the same charge, then I only need 1 of each, correct? So it would be incorrect. So MgO is that formula. It would be incorrect to write Mg2O2, because you could reduce them both easily. This is wrong, so please don't do it. Anyhow, that's it. That's binary ionic compounds. Time to go practice on your packet. Scholar up, Eastview.